we have here another problem. It says a piston cylinder assembly which contains a mixture of 1 kg of hydrogen and 2 kgs of nitrogen. The mixture is compressed in a polytropic process which follows PV to the power, this should be the power, 1.2 is constant. The temperature increases from 22 degrees centigrade to 150 degrees centigrade. We are asked to calculate the heat and work interaction, assuming that the piston cylinder assembly is frictionless. So, we can see how that works. So, we have a piston cylinder assembly which contains hydrogen, which is 1 kg, and nitrogen, which is 2 kg. It is compressed in a polytropic process. PV to the power 1.2 is constant. The temperature initially is 22 degrees. So, I am going to add 273 to it, which gives me 295 Kelvin, and the final temperature is 150 degrees centigrade. Which gives me 323 Kelvin. We are asked to find out Q and W, assuming that the piston cylinder assembly is frictionless. So, we have, for example, a piston cylinder assembly of this kind. Our control mass is essentially the mass here. Okay, this is 423, not 323, that's correct. So, what we are trying to do is find out what happens when this is compressed. So, if it is being compressed, it means the piston is moving this way. The final volume is going to be lower than the initial volume, and we want to find out the heat interaction and the work interaction for this case. So, initially we know the total mass, we know the temperature, initial temperature. So, we can find out everything else, because according to our principle of the two property rule, we have a simple compressible substance. If we know all of the properties of the substances, then it's sufficient to know two properties. So, let us see if that will work over here. So, we know the mass, we know the temperature, and what else do we know? That is more or less what we know. Okay, let us see what we can do. So, let us write down the first law for this. We are assuming that there is no potential or kinetic energy change, because this piston cylinder arrangement is stationary. So, we would normally write this as del E is del Q minus del W. I can consider E to be U because there is no other change. So, and writing in the integrated form, it will give me delta U is essentially. So, this is something which I would know. Now, I know that this is compressed in a polytropic process. I know the CV value of hydrogen, and I know I can find out the CV value for nitrogen also. It's a diatomic gas. I know the molecular weight of hydrogen is 2. I know the molecular weight of nitrogen is 28. So, that is something which I can find out. I know the initial and final temperatures. So, I have a polytropic process which is PV to the power 1.2 equal to constant. We have looked at the work expression in a polytropic process earlier when there is expansion or contraction work. So, the work would be essentially integral of PdV for expansion or contraction work due to a boundary. So, this is what it is, and in the case of P, we can put C by V power 1.2 and we can integrate this to get an expression for the work. So, we have done this earlier. So, this is of the form PV to the power n equal to constant. So, when we integrate it, we get something of the form P1 V1 minus P2 V2 by n minus 1. So, when we integrate this, we essentially get n is 1.2, 1.2 minus 1 is 0.2. So, this gives me the expression for the work which is done. What I also know is that the substances are ideal gases. For an ideal gas, I know that PV is equal to MRT, which means P1 V1 is MRT1. The mass is constant, R is constant, and P2 V2 is MRT2. So, what I can also do is, instead of writing this in this form, I can write this as MRT1 minus P2 V2 is MRT2. I can take out MR constant. So, essentially I have this is equal to, for an ideal gas, MR into T1 minus T2 by n minus 1. This, of course, only this part of it is only true for an ideal gas. This part of it is true for whenever we have displacement work of a simple compressible substance. I can write it in this form only for ideal gases, but in this particular case I have an ideal gas mixture, so that is all right. So, I have this expression over here. I know the mass. So, the mass is 1 kg of hydrogen plus 2 kg of nitrogen, which is essentially 3 kg. I need to find out R. This is a mixture. So, that is R bar by the molecular weight of the mixture. I need to find out the molecular weight of the mixture, which I will do in a similar way to what we were doing earlier. So, this is 1 by sigma of yi by mi. So, yi is the mass fraction. So, I have oxygen, I have in this case hydrogen, and I have nitrogen. So, I have 1 kg of hydrogen, 2 kg of nitrogen. So, this 1 kg divided by the total, which is 1 plus 2, and this is 2 kg divided by the total, which is 2 by 3. And so, I have the molecular weight of the mixture. So, I have this, which is 1 by 3, and molecular weight of hydrogen is 2, plus I have this, which is 2 by 3, into molecular weight of this is 28. So, if I find out the mixture molecular weight, it comes out to be 5.25 kg per kilomole, and I can find out R for the mixture, which is R bar by this, which comes out to be 1583.7 joule per kg Kelvin. So, knowing these values, I can find out the work. So, the total mass is 3 kg. R is what we just found out. This is joule per kg Kelvin into T1 minus T2. So, what was given to us is that the initial temperature is 295, final temperature is 423, divided by n minus 1, which is in this case 0.2. So, we have 1583 . which gives us a value of minus 3 into 10 to the power 6 joules. So, or minus 3 megajoule. So, this is the work interaction. What we were also asked to find out is the heat interaction. So, what we see is that the work interaction for the system is negative, which is what we expect because the volume is shrinking, there is work being done on the system. So, that is negative. So, we are also asked to find out the heat, which we can find out using the first law, which means we need to find out delta U. So, we can find out delta U now. This is the total mass of the mixture into CV of the mixture into T2 minus T1 of the mixture. So, the total mass is known, it is 3 kg. We need to find out the CV of the mixture. So, the CV of the mixture can be found in several ways. We can find out individual CV values on either a mass basis or a molar basis. So, if it is on a mass basis, what we would do is we would do sigma of yi into CVi. If we find out CV on a molar basis, we would do sigma of xi into CVi. So, that is one way of doing it. The other way of doing it is to see what gases we have. So, the gases we have are hydrogen and nitrogen. Both of the gases which we have are bimolecular gases. So, which means the gamma value for both of these gases would be the same. The gamma values for both these would be 1.4, they are both diatomic gases. So, the gamma value is going to be the same. But what I am also given is, so I am given the CV of this. So, I can use that value, or I can, instead of using that value, what I can do is use a mixture and then say CV is equal to R of the mixture by gamma minus 1, where I take R of the mixture, take gamma of the mixture and do this. So, we can maybe do both of them. I will leave some space here to come back for this value and we will look at the CV values. So, I can do R mix by gamma minus 1, and in order to find out R mix, I just did this calculation here, which gave me 1583.7. Gamma is 1.4, so gamma minus 1 is 0.4. So, this gives me a CV of the mixture of 3959 joule per kg Kelvin. What I could have also done is take individual CVs . In this case, the value for hydrogen was given 10352. Find out the CV of nitrogen, which is R nitrogen by gamma minus 1. So, which is 8314.5 divided by 28, which is R of nitrogen, and gamma minus 1 is 0.4, and this would give me a value of 742.36. So, I found both of these on a per kg basis. So, what I can do is now CV of the mixture would be sigma of yi into CVi. So, I have the mass fractions we had earlier. So, mass fraction of hydrogen is 1 by 3. So, 1 by 3 into 10352 plus 2 by 3 into 742. Which gives me 3946 joule per kg Kelvin. if I do not round off the remaining digits, in both the cases I should get essentially the same. So, because I have made slight rounding offs here and there, I get slightly different values, but essentially they should, you would normally get the same. So, this is for example 396 versus 395 is what we have got. So, it does not matter either of the ways, you should generally get the same answer if you took sufficient number of digits. So, we can use one of these values. So, I am going to use it as say 395, sorry not 395, 3959 joule per kg Kelvin. So, I have the CV value here. So, I have the total mass which is 3 kg, I have the CV value which is say 3959, and I have T2 minus T1 which is T2 is 423, T1 is 295. So, this is the delta U. Which gives me a value of 1.52 megajoule. So, this is delta U, and from the first law we have this. So, I have minus 3 in 10 power 6 joule plus 1.5 in 10 power 6 joule. So, this is about minus 1.5 into 10 power 6 joule. So, what we see is the work interaction here is negative because this is being compressed. The heat interaction also is negative. So, because it is being compressed, the temperature of this is increasing, because of which heat is going out of it, is what we have now found. Work is negative because it is compressing this, heat is negative because it is leaving out, and in the process what we see is delta U is positive, which means that the temperature of this gas has increased. For an ideal gas, we know that U is a function of temperature, internal energy is a function only of temperature for an ideal gas. So, delta U has increased means the final energy is higher than the initial energy, which means the final temperature is higher than the initial temperature, which we already knew, because we already knew that the final temperature is higher than the initial. So, which we expected to see an increase in the energy of the gas, which we also have seen.